Okay, so in this video, I will be talking about some search technique improvements, okay, which allow us to prune this search tree so as to decrease the number of nodes that we will be searching and improve and make the searching a little bit faster. Okay, so last time we discussed about negamax and minmax. Okay, so we would be doing a very much common improvement over here, which is alpha beta pruning. Okay, so the basic idea behind as alpha beta is that we have a limit uh, to which we can restrict a player, which is alpha comma beta. Okay, so the optimal value would be one which would be lying between these two bounds. Okay, so beta is the bound which is forced by the player which is standing above that current player. Okay, so this is supposedly this is the minimizing player. Then the maximizing player can force this minimizing player a certain bound. Okay, because it is in the hands of the maximizing player to play either this move or this move. Okay, so if the minimizing player is exceeding those bounds, okay, so if it is exceeding the beta bound, okay, then the maximizing player would simply force the minimizer to cut off that value and return beta from there. Okay, so because it knows that a better score is achievable over there, and if I allow this player to move, then he would force me a score which is more profitable for this player. Okay, but it is not profitable for me. Okay, so he would this player would not consider this that move altogether. Okay, so we will just take a quick look at the pseudocode which I have copied from Wikipedia. Okay, so if first of all we would generate all moves, then we would order these moves. This is an important step which I will discuss later, and then we will set the value to minus infinity. Okay, then for each child node I would try to maximize my current value. Okay, so I had discussed in negamax, the value returned from the recursive call is always negative, because what is profitable for the minimizer is actually a loss for the maximizer. Okay, so these are the relative values. Okay, so we interchanged the value of minus beta and minus alpha and beta over here as minus beta and minus alpha. This is done particularly because we want to set the upper bound of beta as the value which is more profitable for the other player. Okay, so what is more profitable for him is actually less profitable for him. Okay, so this minus alpha would be the upper bound for the minimize. Okay, so then we see if alpha is exceeding beta, and if alpha is exceeding beta, we would cut off over there only, and we will not search the rest of the children nodes. Okay, and we will return the value of beta from that point. Okay, so I will just do a dry run over here. Okay, from minus infinity we would set alpha beta bounds as minus infinity comma infinity. Okay, same would go over here. So these are the initial things. Okay, so now when I reach a depth of 0, okay, so the value returned by this would be minus 5. Okay, so but we are negating this value because the maximizer is of color 1, minimizer is minus 1, maximizer is again 1, and minimizer is minus 1. Okay, so since we are negating this value, the value returned by this is actually minus 3, but it is then negated, so it becomes 3. Okay, so currently my alpha is 3 over here. Okay, there is no beta cutoff because B doesn't have any information about the rest of the nodes right now. Okay, so it can't impose anything on us. The similar will go for this thing. Okay, 5, and then 5, the value returned would be -5, but then it would be negated. Okay, so I'm getting a more profitable deviation over here, so I will update the value as 5 over here. Okay, so these are bounds. Then this would return a value of -5. Okay, this would return a value of 5 over here. Okay, so since it is a profitable value for him, it is not profitable for him, so this alpha would be set to -5 right now. Okay, so we have explored this part of the tree. Okay, now we would move on to explore this part. We would set this bound for maximizer as -infinity, comma 5. Okay, so this 5 tells the maximizer that if you try to exceed this value, then I will not allow you to play this particular move, and the minimizer would push the maximizer in this direction. Okay, so what happens over here is it goes to this and this, and then the value returned over here is -6, and then this value is negated. Okay, so this value is negated, so we have our alpha set as 6, so 6 is obviously greater than equal to 5. Okay, so he knows, this minimizer knows that it is not of any profit to search any further, because the maximizer is able to improve its position in this part of the tree. Okay, so it prunes the search over here. Okay, and returns the beta value. Okay, so beta value would be returned, which is 5. Okay, so there is no improvement over alpha from this position, -5, and then this value returned is -5, which is negated, and this becomes 5. Okay, so this value is then passed to this node. Okay, we have a bound set as -infinity, -5. Okay, so similar thing happens over here. 1 returns a value of 1, which is -1, which is negated by this, and sorry, I forgot to set alpha over here, 5 comma infinity. Okay, so this value is negated, so this is 1. There is no improvement over here. Okay, and the value which is returned by uh, alpha over here, it is again 2. Okay, so essentially no improvement on this side also. Okay, so what I can do is this value of alpha, it would be returned 5. Okay, and this becomes -5 over here. Okay, so I have returned a value of 5 from this position. Okay, so since this value -5, it is greater than equal to -5, so the minimizer knows that this maximizer player, it would not allow it to play any of these moves. Okay, because he is having a profitable deviation by playing this move. Okay, so it is useless to search any further, and it would return the beta value from this position. Okay, which is your -5. Okay, this value is negated, and we have finally your value as 5 over it. Okay, so the score which we achieve by this value is finally 5. Okay, so what the advantage of this thing is, that we have pruned our searches. Okay, so we didn't need to search the whole tree. Okay, for getting the final answer. Okay, so this is an advantage of alpha beta pruning. Okay, so it is more advantageous in case compared to min max algo, where we are searching the whole tree. Okay, so another important thing to note over here is about move order. Okay, so if I have more you know more kind of suitable nodes present uh, present on the bottom row, okay, then I can have a very much good pruning. Okay, so what this means is that if I have some idle value of beta cutoffs, okay, so then I can prune my recursion tree much often. Okay, and more often we have a pruning, much better it is, much faster our search is going to be. Okay, because we don't have to search all the positions in that case. Okay, so move ordering is an important concept, and uh, move ordering depends on the fact that the current player is playing the move which is the most powerful according to him. Okay, so that's why I made a distinction between the moves and the positions on the board. Okay, so I can categorize the moves as more powerful or less powerful based on whether uh, I am getting more score or less score. Okay, so like if there is a queen capture, then it is obviously a more powerful move compared to uh, a quiet move where there is no capture. Okay, so it would depend on multiple things. We would talk about this thing later on. Okay, also. So but what needs to be kept in mind is that move ordering is very much essential. Okay, so if I have a bad move ordering, then it may happen that I have to search the whole recursion tree. Okay, and I obviously don't want to do that in case of chess engine, because you know the increase in the number of moves uh, down as you go down the tree is exponential in nature. Okay, so I could have a million moves and then I could have a billion moves. Okay, so it could increase to that much capacity. So pruning becomes very much important in this case. Okay, so next we would be talking about evaluation functions. Okay, so these are the function which would be called at depth 0. Okay, so if I am searching at 1 2 3 depth, then when I hit the bottommost depth, then in that case I would be returning the evaluation of that particular position. Okay, so what we are going to use is a very basic evaluation function. Okay, so I would be showing that function to you. Okay, so our evaluation function would principally be depending on two things: material count, okay, and the positions in the positions which are present on the chessboard. Okay, so these two values would be the principal things for determining the value of the evaluation function. Okay, so let me show you a simple evaluation function. If you go to chessprogramming.org and you head out to simplified evaluation function, you can find these matrices over here. Okay, so these have values corresponding to each piece for your uh, each square. Okay, so you can just copy these values. Okay, and then depending on where the piece is currently on the board, okay, we can add or subtract these numbers over it, 15 and those things. Okay, so they have considered the queen to be something like, wait one second. Okay, here queen to be 900 and king to be 20,000. Okay, so this table is based on these assumptions. Okay, so you can get an evaluation function, a very basic evaluation function from here. Okay. There are more advanced evaluation functions also, uh, which actually depend on what part of the game we currently are in. Okay. So these interpolate between various phases of the, okay, openings, middle game, and your end game. Okay. So these are called tapered evaluation. Okay. So it would be having a different value for openings, middle game, and end game based on some certain functions. Okay. And neural networks, these have also been employed to get heuristics for these squares. Okay. So right now we you should be focusing on a very basic evaluation function, and try to improve the searches instead of trying to improve the evaluation function first. Okay. So uh, now I would be talking about one of the basic techniques, which is iterative deepening. Okay. So this is a very basic technique, another basic technique for improving alpha beta. Okay. So what iterative deepening does is that it would keep improving the depths. Okay. So till the engine receives a timeout from the user. Okay. Because when you would be, you know, battling an engine with the other engine, then there are time limits for particular moves. Okay. So we can't exceed those time limits, and we have to return a value in that much bound. Okay. So if like my time limit is 3 seconds, then I have to return the best value that my engine was able to find under 3 seconds. Okay. So if I arbitrarily assign a depth of 8 and try to search to that much depth, and probably there are millions or 10 million node present at that depth, and I'm not able to find the value, then the engine will essentially fail in that case. Okay. So what iterative deepening does is it evaluates the positions at successive depths. So 1, 2, 3, 4 till we receive a timeout from the user. Okay. So principally this has two benefits. Okay. So the obvious one is if there is any timeout, then the engine knows which move to play next. Okay. And then this thing massively improves the alpha beta algorithm by move order. Okay. So what I get to know is the best moves which are possible at a particular depth. Okay. And as I said earlier also, if the maximizing player plays the best move which he thinks is the correct one, then uh, there are more chances of this the final node to be more ordered. Okay. So we want move ordering because we want to prune a tree and save the time uh, which would otherwise be wasted in exploring all the nodes. Okay. So these two advantages, these outweigh the disadvantage of successively searching each node. Okay. So another thing is at each depth we are calculating the score of each move. So we are again massively improving move order. Okay. So we will be seeing some improvement techniques like killer heuristics and principal variation move ordering, uh, and transposition table, which would be able to utilize uh, the information the from the previous depth and apply it to the next depth, so as to improve your move order. Okay. So uh, since uh, we are over here. It makes sense to add some more information to a game state. Okay, first of all, we would be adding a key. Okay, so this is a 64-bit unique integer which corresponds to each position, so that we can hash these value later into a transposition table. Okay, so this 64-bit unique integer, uh, this can be obtained by hashing several values which were there in this structure. Okay, so this game state, these values recognize the state of the game independently. Okay, so any game would be having uh, these values uniquely. Okay, we can ignore the material since this can be calculated, and this inverse mapping. Okay, because these are just utility functions and this king square. Okay, but this uniquely identifies uh, a position. Okay, uh, a game state, a position or a game state. Okay, so the number of the way the pieces are present on the board and which side is to move, and the number of half moves and full moves. Okay, so these things identify a game state uniquely, and these values can be XORed to get a 64-bit integer. Okay, so I won't go much into this detail of how it is obtained, but you can use bit manipulation techniques by moving these uh, these values towards left and then XORing all these values together. Okay, so by in that way you can get a unique 64-bit integer. Okay, which would represent the whole board uniquely. Okay, so next we would have an hash table. Okay, so this table will hash the keys and the corresponding move into a finite space key using modulo. Okay, so what happens is that number if I'm trying to store all my 64-bit integers over here. Okay, then it would be very much expensive to the memory. Okay, so since I can't afford this kind of memory, I have to restrict uh, myself to a finite memory using modulo. Okay, so each position, uh, the engine is trying to remember each of the position, and the score which the score sorry the best move which is possible at that current position. Okay, so if I would later want to if I later encounter that position in my game, then I can directly refer to my transposition table instead of searching the whole game tree again. Okay, and then it has further flags. These are the flags HF beta, HF alpha, and HF exact. Okay, so this represent HF beta represents that we had a cutoff at that particular point. Okay, so the value which we got was actually a beta cutoff. Okay, and not the exact value returned by the evaluation function. Okay, and then again this HF alpha represents that the evaluated value was lesser. Okay, so we returned the alpha value which was more than uh, uh, your evaluated value. Okay, and this HF exact represents that on playing this move we are getting an exact evaluated value. Okay. Okay, so regarding the hash table and transposition table and these flags, I'll be talking later on. in detail. Okay, so next we move to principal variation. Okay, so this is an array which would contain the sequence of moves which the engine considers as best for a given depth. Okay, so this also very much helps in improving the move ordering, because we are considering the moves which are better one at the above depth to be played first. Okay, so like for example, if we have this tree. Okay, so the principal variation array would be containing these moves in sequence. Okay, so these moves would be played by these moves would be contained by a principal variation array of size 3. Okay, then we have our history. Okay, so this may be added optionally, which is nothing more than an array containing sequence of moves which lead to the current state. Okay, so we will have just an array of history. Okay, so this would be storing moves. Okay, which are updates to a game state, and these may be anytime referred for telling what was our position uh, in the game before that particular final position is reached. Okay, now another important thing that I want to talk about is horizon effect. Okay, so what happens is, if we limit our searches to specific depths, then this may lead to strange behavior and the engine may worsen its position further. Okay, so I have written an example. An example may be sacrificing a rook for a queen when queen capture was inevitable, but engine could not determine it due to the horizon effect. Okay, so a more simpler example would be like a queen is capturing a pawn. Okay, then a pawn is sitting over here, and it captures the queen. Okay, so I have lost a queen when I have uh, by just moving up a pawn. Okay, so this is obviously a bad move. Okay, so uh, so this may happen that the engine is not able to determine this because due to the depth limitations of the engine. Okay, so these type of error may be mitigated by using Quiescence Search. Okay, so where the engine would first search for the capture positions. Okay, so all the positions which are causing capture at a particular all the moves which are causing a capture for a given position, those moves would be evaluated to maximum depth till we are done with such moves, and then the engine would return a score. Okay, and return the best move that must be played. Okay, so uh, I would so the Quiescent Search, helps in overcoming horizon effect. Okay, so as I had explained earlier, also terminating search while captures are left is very dangerous, as we can't see after this step. Okay, so we must extend our search till all the captures have been done. Okay, so a little bit of code over here I would like to show. Okay, so this one. Okay, yeah. So we have a Quiescent Search over here. Okay, so if I see the alpha beta algo currently, then what it does initially is that it returns evaluation position, but since that is dangerous, I have replaced it with a Quiescence Search. Okay, so a Quiescence search is nothing but a search where a search similar to your alpha beta algorithm, where we evaluate all the capture moves. Okay, so these capture moves are the moves which are creating a capture. Okay, so as we had defined earlier also in this moves structure, the captured piece. If there is some captured piece, then only we will be making that move in Quiescence Search. Okay, so all the capture moves would be generated. Okay, and then using an algorithm similar to alpha beta, we will be picking we would be evaluating these positions. Okay, till no capture moves are left, or the current evaluated score of the particular position it exceeds the beta cutoff. Okay, so if it exceeds the beta cutoff, we would be returning that score, because the minimizing player would never allow us to play that. Okay, so it doesn't make any more sense to go deeper into that tree. Okay, so similar, the code is very much similar. There is a similar function as pick next move. Okay, which picks the best move. Okay, from so as to improve a move order. Okay, so this is Quiescence Search. Next we will see some other move ordering techniques. Okay, so this is also an important part. So first of all is principal variation. Okay, so this principal variation we can extract this from a transposition table. Okay, so I would be discussing this after I have discussed transposition table. Okay, but I will give you an idea. Principal variation is nothing but these set of moves which result in the best score at the previous depth. Okay, so if I have my hash table present, then if I am retrieving from that particular hash table, supposedly this is position. Okay, so the position key is hashed with the corresponding move. Okay, so I'm retrieving the best possible move corresponding to, in the hash table I have I will always store the move which is the best possible move to be played at that particular position. Okay, so since it does not make any sense to evaluate moves which are less better at that particular position, so in this position the best possible move is this. Okay, so what a principal variation search will do after we have evaluated this whole depth, this depth of 3 by alpha beta, is that it would see the best move from here. Okay, and then play that particular move, so that we reach at this particular position, and then at this particular position we will again search for the best possible next position from this place, best possible next move. Okay, then we reach here and here. So in this fashion we are getting the move in our principal variation array, which is the best possible set of moves. Okay, so in the move score, in the list of moves, okay, where we are maintaining the moves and the corresponding move scores, we will give a higher score to these moves. Okay, so like we have a generate moves function over here. Okay, then we have order moves. I will show you this in code. Okay, so I don't want to scare you by showing the code, but it is simple if you look at in parts. Okay, so like I have generated all my moves over here. Okay, and I have got my principal variation move by probing the hash table earlier. Okay, so here I have probed my hash table, so I have my principal variation move present over here. Okay, so I don't need to use an array, because by probing the hash table I am getting the best possible move. Okay, so If principal variation move is not equal to no move, then I will iterate over the list of the move that is generated by generate all moves function, and then I will score these moves as high as possible, in this case, which is 2 million, and then I will break out of the loop. Okay, so these scores would be considered first compared to other moves, which I would have scored lesser. Okay, so, and this is the basic idea behind principal variation. And then the next technique is your most valuable victim and least valuable attacker. Okay, so these are essentially for capture moves. Okay, so the principal variation covers both the best move and the both the capture moves and quiet moves. Okay, this is something which is related to capture moves only. Okay, so in this case, what happens is that we rank the pieces according to the most valuable victim and the least valuable attack. Okay, so if I have something like a queen and a pawn, okay, so this must have a lower score than a pawn into pawn. Okay, and these should have a lower score than a queen into queen. Okay, and this must have a lower score compared to a pawn into queen. Okay, so on my left side, these are the attacker pieces. Okay, and these are the victim pieces. Okay, so obviously if the victim piece is more valuable, then this must result in a higher score, and that victim piece must be captured by a less valuable attacker. Okay, so that move would have uh, more amount of score. Okay, so this technique we will use. Basic formula is somewhere here in the code. Okay, so we can use this formula for filling out our array. Okay, so 13 into 13 we have considered over here because it is about a null piece also. Okay, so first piece we have considered to be a null piece. Okay, and the rest of the pieces are the 12 pieces which are found on the board. Okay, so we have a corresponding array over here, and then when we are generating our moves, and if the move is a capture move, then in that case we can just score that move using this table. Okay, so MVVLA table, we can score that move. Okay, so after this we have our killer moves. Okay, so these moves are for quiet moves. Okay, so basically the killer moves are the moves which lead to a beta cutoff. Okay, so if I have a two good position present somewhere on the tree. Okay, supposedly this is this is my tree. Okay, and I have got some beta value from here. Okay, supposedly this value was 5. Okay, and 5 sorry, I've got some alpha value from here. Supposedly this value was 5 and this value was infinity. Okay, so in this part of the tree, this value will be minus infinity and minus 5. Okay, so if I get a too good move from over here. Okay, uh, if I get a too good move over here from here for the minimizing player, supposedly it is minus 4, then in that case it would lead to a beta cutoff. Okay, so this kind of move would be called a killer move because it is a too much good move, and this your uh, maximizing player would never allow this player to play this move. Okay, so in this case I have got this move from my first recursive call into this depth. Okay, but supposedly this move was present somewhere here. Okay, and in case of chess engines, the number of moves generated is huge. Okay, so there can be a lot of branches over here. Okay, so if this move is present anywhere later in the tree, then in that case uh, a very good a very good pruning move could have been avoided. Okay, so what happens is that we have we have explored so many nodes, and after that we are finding that the minimizer was having some good move present over here, which the maximizer would not have wanted. Okay, so if that move was present in the starting only, then it would have seen this move, and it would have pruned these all moves. Okay, so it it would have resulted in a lot of enhancement for the search engine. Okay, so that's why it is important to keep note of the killer moves. Okay, so these moves are recorded a little below these MVVLA moves. Okay, because uh, these uh, these moves these moves are only effective when we have a beta cutoff value already present with us. So this is the rationale behind this. And killer moves are usually indexed as your an array of size 2 with corresponding depths. Okay, so usually we keep only the top two moves. Okay, at each depth. Okay, because there is a limitation. We can't store all the moves which we get at each depth, because the number of moves increases exponentially. So in general, it is a practice to keep only top two killer moves with us. Okay, and then after this we have our search history heuristics. Okay, so these are all the moves which did not beat beta. Okay, so these are not killer moves, but these moves led to an improvement in our alpha score. Okay, and again, these moves are obviously the quiet moves. Okay, because the capture moves are already scored very much higher. So uh, we first check that the current move should not be a capture move. Okay, if we are noting it in search history heuristics. Okay, so I would just show you some code over here. mm, Wait 1 second. Okay, so we have our killer moves over here. Okay, so these killer moves corresponding to index and the ply of the current search. uh, we are in the zero position. We are keeping uh, the best possible move. Okay, so the that uh, there is a matter of observation that as we move as we explore more of the tree, then we would be getting more and more better moves. Okay, because we have more information about about the tree at a given stage. Okay, so any move which is explored later on in the tree is going to be obviously better than a move which was explored before. Okay, so that is the reasoning why we are keeping the move which is explored later uh, in our search killers. Okay, at zero index. Okay, so this is the topmost index which is going to have more score, something kind of 800,000. And this second index, which is one index, this would score this would keep the previous score with it. Sorry, not the score, the previous move with it. Okay, so the killer moves are only noted when a score is exceeding beta value. Okay, so we will score these moves. Okay, and then we have our search history heuristics. Okay, so search history heuristics, these are stored by the uh, pieces and the two square. Okay, and these are scored as our depth increases. Okay, so what that means, what that implies is that uh, when we are generating the moves again at some other position, then in that case we would uh, be scoring those moves by depth. Okay, so whatever you are seeing over here, wait 1 second, where is it? Okay, so whatever scoring that we are doing, except the PV move scoring is only for the later positions. Okay, so these scorings at a particular depth, we have generated all the moves. Okay, so uh, wait 1 sec. Yeah, so we have generated all the possible moves. Okay, and we in this part, and then we have scored those moves in terms of PV moves. Okay, uh, the scoring which is being done in this function and in this part only. Okay, this part is not doing the scoring of the moves. Means this part is storing the best possible moves for the future. Okay, so uh, I can't apply this to the current depth. Okay, so this is storing these moves for future references. Okay, so this also plus equal to depth, this is being stored for future reference. Okay, so whenever again we call the generate all moves function, then when it is adding your quiet moves, then in that case it would score the moves uh, which were killer moves as 900,000, and the second one as 800,000. Okay, and if it fails to find them both, then it would be scoring those moves which improved our alpha. Okay, so in this case it is given by your pieces and the two square where a particular piece is moving. So if uh, none of these moves match a killer heuristics, then we would apply search heuristics over here. Okay, so search heuristics are not incredibly important, and some people claim that they cause nothing more than noise because we have our pieces, uh, we are indexing by pieces and two square. Okay, so this is nothing very much unique over here. Okay, and but there is some argument that since we are ordering scoring this search heuristics according to the depth of the search. Okay, so the nodes which are closer to the root uh, are getting a higher score compared to nodes which are closer to the leaf. So it may be somewhat more uh, it may be more helpful. uh, it may be correct in that sense. Okay, so that is the argument in case of your history heuristics. Okay, because the main problem here is only about these clashing values of the pieces. Okay, so it may happen that we have searched we are taking inspiration from positions which were not similar to a particular position. Okay, like if a queen was present somewhere at a particular if a queen had to go from one position to the other position, okay, then at that particular 2 square we are placing that queen, okay, and it may happen in another position that the queen is going to that square only, okay. So uh, that is an argument against this, that it is just generating random noise, okay. But usually these heuristics values, they are replaced as we are searching, okay. And the positions, because the search works we are moving up the tree at each successive up the recursion tree at each successive step. So the node which is more closer to the root node, generally it is only played, okay. So this may have search heuristics may have some merits in that case of argument, okay. So uh, these don't produce a lot of difference in the number of nodes which we are evaluating search heuristics. So this may be skipped if you are implementing chess engine for the first time. But killer heuristics are very much popular, and they do produce uh, comparatively much less node, if you are having a node search of 46,000, then the killer heuristics may bring it down to 36,000, okay. So and similarly in case of search heuristics, the degrees may be only of 3k instead of 10k, which you are getting in the case of killer search, okay. So we are done with search heuristics. And next we would be talking about transposition table, okay. So what basically a transposition table does is, at a particular game state, it hashes the best value of the move, okay, so that we don't have to search again the game tree all over, okay. So if I have a best move at a particular position, then I can simply return this move if the depth of your uh, previous search is greater than the current search which you are searching for. What it essentially means is that if you are searching supposedly this tree, okay, and we uh, we encounter this node, okay, and this node we have this position resembles a position we had already searched before, okay. So supposedly at that point of time the function searched to a greater depth, okay. So there, in that case only, it is useful to return this value back, okay. If the search depth is greater than equal to the current depth the function is aiming to search for, okay. Else it would result in only errors, okay. And we have three flags over here, okay. So these are hf exact, hf beta, and hf alpha. So hf exact implies that for the current position, if we are storing a particular move, then the score corresponding to that move would be an exact score, okay. So that score has been evaluated by going to the bottommost depth, okay. Then secondly we have our hf beta, okay. So this is a score which is actually the upper bound, okay, which the other player was imposing on this particular player, okay. So uh, what if the player is playing a move which is resulting in a higher value. Okay, so it is resulting in a higher value which is exceeding the beta score. Okay, so in that case, what the hash function will do is that it would score that particular move and the beta value along with it. Okay, so this tells us that the beta cutoff it was reached at this particular position. Okay, and then we have our HF alpha move. Okay, so HF alpha flag is set when the current value is not able to beat a lower bound, which is alpha. Okay, so in that case, only the alpha move is the move which is played. Okay, so uh, I would be showing some code for hash function. Okay, so first of all, there is your code for storing hash entry. Okay, so these uh, first of all, we would determine the index for storing this hash entry. Okay, which is uh, nothing but a modulo by number of table entries, so that we have a restricted size of the table and not an infinite size table. Okay, and then this is for meeting situation. Okay, not so much important for explaining the store hash entry, but basically it is uh, telling about in how many applies we would get a mate score. Okay, so next we have an important thing over here, that in that particular index we are storing the move. Okay, and then the position key. Okay, flags the score and the depth of the search. Okay, and then when we would be probing the hash table, we would again determine that particular index. Okay, and we would check if the position key is matching the current position key. Okay, and if it is matching the current position key, then uh, and if the current the depth of the search is greater than equal to this depth, then we can process this thing. But first let me talk about this. We would store this move. Okay, so the move in the hash table, it would be stored. It doesn't matter. This move is useful because if uh, because it would be the best move from that position. Okay, because the hash table is storing only the best possible moves. Okay, so if also the depth is less than the current depth of the search, then also we can utilize this move for our move ordering, because this was the best possible move which could have been played in an earlier depth. Okay, so this is something similar to your probing of principal variation. Okay, so this is a principal variation move essentially. Okay, so if we uh, get to if the depth is greater, okay, then we would store the score for this current hash entry. Okay, and then this is again checking it made conditions. Okay, so we would be returning the scores accordingly. Okay, the important part is over here. uh, we would be switching for the flags. Okay, so if we have an HF alpha flag, okay, then what we know is the current score is nothing but the score in the hash table is nothing but a hash entry which corresponded to the lower bound at that particular position. Okay, so we will check if the score in the hash entry is lesser than the score of uh, of current alpha. okay, because there would be some alpha for that alpha and beta values for that particular node. Okay, so if it is less than equal to alpha, then we can obviously improve our score by playing the other move. Okay, so we would store the score for this alpha search and return true. Okay, so I would tell you what this return true means later on. Okay, so we have this return true implies that we were able to find a move which was at a greater depth, which had searched at a greater depth. Okay, so we can essentially return this code, okay, along with the move that was played, okay, at that particular position, and we can get our evaluation without having to further go down the tree. Okay, then we have the HF beta case. Okay, so if it is HF beta, then the score stored in the hash table was a score which was an upper bound. Okay, so if this score is greater than equal to your beta score, then in that case the algorithm will do nothing but store this beta value, because this is the current upper bound which has been imposed on that particular node. Okay, so it has to store that beta value, and this search, if this part would have been searched, if that node had been searched, then that node would have essentially been pruned only. Okay, so basically in both these cases we are not searching our node. Okay, we are not going further down the tree. Okay, so these values, we are not going down the tree, we have just got our scores. Okay, and then we are just complying with the alpha and the beta values. Okay, because these scores which I have stored in the transposition table, these are not exact scores. Okay, so HF beta and HF alpha, these are not exact scores. Okay, so I can't just return these scores and say that I was receiving something like this from my game tree, which was you know at the down of at the bottom position of that node, or at greater depth from that node. Okay, so basically these HF alpha and HF beta values, these are dependent on the other nodes. Okay, so if I'm not able to beat the current beta with my previous score, okay, then in that case I have to search the whole tree again. Okay, and similar goes for my HF alpha value also. But if I have an exact value, then I can determine that yes, this was the score which was received at my particular node. Okay, so then I can blindly return true value. Okay, and then finally we have return false over here if any of the above conditions these are not met. Okay, so this is about probing the hash table, and I will show you how these hash entries are being stored. Okay, so what we are doing over here is that okay, first example is over here. So if a score beats beta, okay, and the score obviously beats alpha, then we have updated our hash entry, okay, with current position, the best move, and HF beta flag. Okay, so this depicts that we have the move that the other moves would be pruned after this. Okay, so the score which we are getting is not an exact value. Okay, so this is the beta value actually. Okay, so similar goes for our alpha value. Okay, if alpha is not equal to my old alpha, then in that case I can blindly store the value of alpha. Okay, because I have gone down to a certain depth, and then I have calculated my best score. Okay, else I have to store uh, an HF alpha flag along with an alpha value. As I'm just getting a lower limit over here, which has been enforced onto me by a node which was present somewhere at a higher position. Okay, so if I like if I am storing an alpha or beta value over here, then this value this has been enforced by a value which was somewhere here, or this particular value. Okay, so this value is not an exact value that I'm storing at this position. Okay, so this is all about transposition table. And then finally move to null move pruning. Okay, null move pruning is also a fantastic technique. Okay, so uh, I've seen in if you go to depth 8, then sometimes in one position I was encountering 21 million nodes. Okay, and just by applying depth move pruning, I was able to greatly reduce it to 3 million nodes only. Okay, so it is a fantastic technique. Okay, so in this technique we give the opponent a free chance by not playing a move and see if we are strong enough. Okay, so what happens is in this technique is that we make a null move. Okay, so a null move is not allowed in chess, wherein you give a free chance to your opponent to play a move. Okay, so the opponent has a free chance to play a move. Okay, so whichever player is playing a move, he that player is considered to be stronger compared to the other player. Okay, since he does not have any limit over the beta cutoff. Okay, so that player may maximize its value to the maximum potential. Okay, so we essentially give a free move to the other player, and he can and we search the evaluation for that particular player at a reduced depth. Okay, so it is like saying that giving you a free chance to hit me. Okay, and if you are not able to hit me in that case, then I would surely win the fight. Okay, so uh, this is the reasoning behind this. So the basic assumptions are that there is a disadvantage of forfeiting one turns, uh, and it is greater than the disadvantage of performing a shallower search. Okay, so essentially what we would be doing is that we would be giving the other player a free move, and then we would make a shallow search. Okay, so a shallow like if we had a search for depth 8. Okay, and if I give my opponent a free chance, okay, then in that case I would the opponent would just search to a depth of 4, supposedly to depth of 4. This depends entirely on what we allow the opponent what depth we allow the opponent to search. Okay, so the advantage of giving a free move to the player is compensated by the disadvantage of performing a shallower search by the opponent player. Okay, so this assumes that null move will produce a cut off frequently enough to justify the time spent performing null move searches instead of full search. And in practice, this has also been usually found to be true, because at a particular chess positions, there are many moves which are kind of redundant. Okay, so uh, it doesn't matter if you uh, allow the other player to perform a free move in those cases. Okay, so I will show you a simple code, a simple pseudocode for this. Okay, so if depth is 0, then we would return the evaluate function. Okay, and then we would make a null move. So essentially what this function does is that it switches the side. Okay, and the current side will not make any move, and then we would do an alpha beta search with the alpha value set to minus beta and the beta value set to minus beta plus 1. So the basic logic behind this is uh, to decrease the window size. Okay, so I have my window size as minus beta and minus beta plus 1. Okay, so this beta value is a value which the player which is at a depth just at a successive depth higher than me can enforce over me. Okay, so I'm reducing the search window size to only minus beta and minus beta plus 1. Okay, so if this player is able to improve his or her beta value to even by even 1, then in that case if in that case I would be getting a value. Okay, if the alpha is improved beyond beta plus minus beta plus 1. Okay, so supposedly if I take the value of beta to be 100, okay, then this would be minus 99. Okay, and this would be minus 100. Okay, so if this becomes minus 99, okay, so minus 100 can go up to minus 99 max to max. Okay, so this function is returning the minus 99. Okay, so the value would then become 99. Okay, so my value has actually decreased if I let it the other player move. Okay, so if my value has decreased, then this means I can't afford to give him a free null move. Okay, so I'm not in a very much good position, and then I have to search again uh, by generating all the possible moves. Okay, and the other thing to notice is that we are reducing the value of depth over here. Okay, by depth minus 1 minus r. Okay, and if this value is greater than equal to or beta value, okay, then the minimizing player it would never allow us to play this particular move. Okay, so this move is too good for the minimizing player uh, for the maximizing player. So the minimizing player would never allow such a move. Okay, so in this case we would just simply return a beta value. Okay, so this was the important thing. And one other important thing to keep in consideration is that we should not have two successive null moves. Okay, so because this function is recursive in nature, so it may happen that uh, the search function uh, tries to do null move pruning again and again, and which may not at the end result in any actual search. Okay, so this was a good this was a thing to note. And then null move pruning fails in few cases. Okay, so it would fail if your king is currently in check. Okay, because in a case of check, the opponent piece would simply eat up the king. Okay, because it is the piece with the most value. Okay, so the game would go haywire from over there. So it must not be allowed in positions where we have a check. Okay, so if you are currently in check, then you can't afford to give a free null move to the opponent. And the other places in the case of zugzwang. Okay, so now what a zugzwang position is, that it is a position reached where uh, a particular player would want to skip his position. Okay, because moving any of the piece would result in a further deterioration of the position for that particular piece. Okay, so for example, if I'm evaluating from the side of the black king. Okay, and then if I give him a free and if I give the opponent a free null move. Okay, so the opponent say moves over here. Okay, so if I'm searching, then I can then move my king over here, and this becomes queen, and then eventually this white king will get checkmated. Okay, but in reality this game is moving towards stalemate, because if white moves to any other position, then uh, if black moves to any other position, then the white king can simply eat this pawn. Okay, so what my null move pruning over here is telling me is that any other move is a good move for the black king, but in reality this is not the case. Okay, so this is a minor disadvantage of null move pruning. So that's why null move pruning is not evaluated in endgame positions, because it fails to realize zigzag positions. Okay, uh, so we are now done with our discussion. Let us just recap what all we have seen over these slides. Okay, so we talked about search techniques, alpha beta. Then we talked about iterative deepening, Quiescence Search, more ordering, and then most valuable, least valuable attack victim, most valuable victim, and least valuable attacker scheme. Okay, then we talked some about killer heuristics, principal variation, and then finally about null move pruning and transposition table. Okay, so even if you implement these techniques and try to make a search engine from this, then you can easily achieve a CCRL rating of 1500. Okay, so if you translate this to your fight rating, then it comes out to be somewhere between 1500 to 2000. Okay, so you can make a chess engine by using a very basic evaluation function which beats around 90% of the chess players around the world. Okay, so definitely this chess engine can be further improved. Okay, so some techniques that I know about and that I left were about improving the evaluation. Okay, so a tapered evaluation function is a much better function than the basic evaluation. Okay, then bit boards, and these are also this is also very much useful, book openings. Okay, so if Otherwise, what the chess engine does is that it makes random moves. Okay, if you don't provide any book openings. Okay, and then finally the end game tables. Uh, the search engine can be very much faster if it is referring to them, and these end game tables have been I think solved for 4 and 5 pieces. Okay, uh, 4 and 5 pieces. I think the end game tables have been solved. 6 pieces end game and 7 pieces end game table. These would not be possible in the near future also, because the capacity required for storing these is in petabytes, I think. Okay, so these evaluation improvements you can do, and if you want to refer any further, then you can always head to chessprogramming.org, and there is a detailed playlist from where I have copied most of this code from. Okay, it is a playlist by Blue Fever Software. Okay, in his playlist for 95 videos, I think this is this is now number. He explains in very much detail how to make a basic chess engine. Okay, so you can always refer to those videos. Okay, I will provide a link uh, uh, at the bottom for those videos also. Okay, so thank you so much for listening and your time.